until now we were looking at regression as a general regression problem. We did not actually assume any form of the regression model. We did not assume any form of y of x. Now what we will do is we will assume a particular form, specifically the linear form, and then we will try to understand what kind of solutions we can get for that linear form. Now before that, it is important to understand why the linear form is used. Okay, so the linear form is quite simple. So as you can imagine that it is as straightforward as the equation of a line, which is y is equal to mx plus c. But we will not use this form. We will use w's to denote weights. Okay? So what we will write it as is y is equal to w1x plus w0. Okay? Even simpler model would be y is equal to w0, where y is just a constant, and that's the simplest model that you can have. But we will make it slightly more interesting so that it varies with x. So we will make it y is equal to w1x plus w0. Okay. And the way we will write this is we will write it as y is equal to dot product of w and x. Okay. So we don't want to deal with w0 as a separate entity. So we'll try to absorb it in the w itself. So before we can do that, we will express x with one additional term, and we will call it x dash. Okay. So here, let's say if we have x is multi-dimensional, so we have x2, x1. We will add a particular number to it, which is 1, and now we will call this x dash. Okay. So this particular vector allows us to simply absorb w0 in the w vector. So your equation would become y is equal to, let's say if you have d dimensions, w d x d, w d minus 1 x minus 1, all the way up to w1 x1 plus w0 1, which is part of that x dash. So basically the form of the model that we'll deal with is w dot product with x dash, or another way to write this is using these angle brackets, w comma x dash, or you can also write it as w transpose x. All these are interchangeable terminologies, notations that we will use. Now the reason we study this linear model is because it is analytically one of the simplest models, and it is very well understood. The math behind it is quite inspired from probability theory and linear algebra. So we can get ideal solutions for this problem given a set of data, which means we'll also have a set of target values, not just x, and so we'll have some target for the y. Okay, and the other reason we studied this is because it's the foundation for more complex models via concepts such as linkage functions and so forth. So to give you an example, let's look at different ways of looking at the linear model. So what we can do is, let's say we want to fit a polynomial model for a single variable. So instead of xd, what we will have x to the power d. So we will have x to the power d and then wd plus x wd minus 1 x to the power d minus 1, right, all the way up to w1 x to the power 1 plus w0 x to the power 0, which is 1. Okay. So this can model a polynomial of x, and now we have a nonlinear function. So we can think of different ways of defining these dimensions of x, which could be, for example, powers of a single variable, or these could be some basis functions such as Fourier basis functions, or these could be kernel functions such as the radial basis functions. So based on that, we can model nonlinear functions so long as we have fixed functions that are extracted and put inside this feature vector x. So we will use X as a catch-all for not just multiple dimensions, but it could be multiple features as well. So now let's look at linear function and its one optimal solution. Okay. So basically what we have is y is equal to w transpose x. Okay, so this x is bold, w is bold because both are vectors. Okay, because we have multiple dimensions of x, and those could be either derived from a single underlying variable by extracting powers or by extracting kernels or and so forth, or they could be genuinely different variables. We don't care at this point. We just are saying that y is a single dimensional variable. Y belongs to r to the power 1, whereas x and w belong to r to the power d. Okay, d is the dimension. Now we have this, but we also have a target value t. Okay, and all these can have these indices I, because I ranges from 1 to n. We have n different training samples. Now here, keep that in mind that w will be the same for all training samples. That is the model. The model itself does not change between different values of I. So now basically what we have is we assume that this target value t is actually equal to y plus some noise. Okay, and we will assume some distribution for the noise. So what we want to do is, if we want to minimize the expected value of t minus y to the whole squared, we are actually minimizing the variance of the noise. So let's say if we want to minimize the expected value of t minus y whole squared, that is equivalent to basically the expected value of noise squared. Okay, so that is the variance of the noise. Now why is it the variance of the noise? Because we can easily prove that this noise better have a zero mean. If it doesn't have a zero mean, then we will not be able to minimize the sum of squared errors or the mean squared error between t and y. Okay, so that is basically basic math, that the noise has to be essentially zero mean. Now because it is zero mean, we don't worry about the mean, but let's look at the variance. Okay, so now let's assume that this noise has a particular distribution. So let's assume that this noise is actually drawn from a Gaussian distribution. Okay, for Gaussian distribution we'll write this stylized n, and what will be the mean? The mean will be 0, and we will have some variance. Okay, and we will call it sigma square. So and we don't know what that sigma square is. We just know that we can estimate it, but we don't know what that is right now. But essentially the best estimator that we will have for any given t is that something that will have zero mean. Okay, that is pretty much given. So now let's look at the probability distribution of t given x, okay, and some weights w and this sigma square. Okay, so what is, let's unpack this this expression a bit. Okay, what is the probability value of t? The probability value of t means that under this given model, right? So under this given model, what is the distribution of t, right? And what is the model? The model is based on the weights w. Okay, and there is an assumption of an underlying variance of the noise sigma. And what is this capital X? Capital X is basically the entire data matrix. Okay, so the way we will write this data matrix is that this X is equal to so each because X is a vector, we will arrange it in rows. Okay, so we will have x11 all the way up to x1d. This is the first data point, right? So here we have d dimensions of the first data point, and then we will go all the way down and we will have xn1 all the way up to xnd. Okay, so we have n data points, and that data point is in the last row, and it is expressed as follows. So basically what we will get is, now what is y? Y is how many dimensions? Y itself is n dimension, so y is n cross 1. and the way we will write it is it will have this X matrix which will be n cross D, okay, and times W. Alright, so W will be this is all of these are now vectors, even Y is a vector here, so I'm writing bold Y, okay, and this is a bold X because it's a matrix, and this is going to be D cross Y. So basically this is what we are trying to estimate the W for this, so that we can reduce the sum of squared errors between Y and T. Now T itself can be a vector because we will have the n samples for T. So what is our objective function? So first of all, let's see what our objective function is should be. Okay, for that we will try to first take a probabilistic view, and then we will come back to this. So to take that probabilistic view, let's look at the probability of T. We want to maximize the probability of T given X. We want to maximize the probability of T given X. Okay. And what is that probability? So now we will make another assumption, and that is the IID assumption. IID means independently identically distributed. So any T that we draw given X, that will be so it will depend on X, but it will be independent of other T's that we have drawn, and it will be identically distributed if we draw the T for the same two different T's for the same given X. Okay, so the assumption of this IID is this IID assumption is quite important for unpacking this distribution. Okay, so here what we will do is that now this is the T vector and this is the X matrix. Okay, so here, because every T is independent of the other T, basically this expression will be equal to product of all the probabilities of I is equal to 1 to capital N. Okay, why? Because for each T the distribution is independent of other T's. Each Ti, the distribution is the probability is going to be independent of the other Tj's. So we will have P of Ti, okay, given Xi. Now it doesn't depend on other X's because it is identically and independently distributed with respect to other T's. Alright. So now what is this probability distribution? So this is going to be, it's going to be a Gaussian distribution. Okay, and the mean of that Gaussian is going to be precisely what we estimate, right? So that is going to be this W transpose Xi, alright, and the variance is going to be the noise variance, which we assume to be sigma square. Alright, so we want to maximize this. Now what is the formula for this Gaussian distribution? Right. So the formula for this Gaussian distribution is going to be it's going to be 1 over 2 pi sigma square root, okay, and then we will have e to the power, okay, or let me just call it exp, it's easier to write it that way, minus 1 over 2 sigma square. Okay. And then I will have the mean, I will have Ti, okay, minus the estimate of it, which is W transpose Xi, okay, whole square. Now if I want to minimize this, I can also take the, sorry, if I want to maximize this, why do I want to maximize it? Given the model, I should have high probability for the values of T that I have observed. Okay, if I don't get high probability for the T's that I have observed, then my model is not very good, right? It is giving me very improbable values of T. It will give for the given T is very improbable given the model, right? So I want to maximize this probability, and when I want to maximize a function, I can take a monotonic function of that function and maximize that. So I will take log of this and maximize it, because then I can convert this multiplication into summation, and it's easier to deal with those summation. right? Plus the exponential term that you see, that will become something that is easier to deal with. So instead of this, I will maximize the log probability of P of t. T is a vector here given x. Okay, and because of that, I will let me neglect all the constants. So basically it will be equivalent to maximizing. Okay, finally what we will get is we will be maximizing the sum of, okay, I is equal to 1 to n, and it will be negative sign here, ti minus w transpose xi whole square. Okay. So what does that mean? So this because I have a negative sign, it will become a minimization. So basically this will be equivalent to minimize over what? Minimize over different values of w. Find the w that will minimize this sum of squared errors. Okay, so we want to minimize this for sum over all the training points. Okay. So that's how, with the Gaussian assumption around the residuals, with a Gaussian assumption around in the noise in the of measurement of t, what we will get is when we try to find the maximum likelihood model for linear regression, we will get something that will be quite easily interpretable as minimizing the mean square error or the sum of squared error of the training points. Okay. So now what we need to do is we need to take so let's call this the loss function, loss of w for any w, and if we take its derivative with respect to w and set it to 0, what we will get is the maximum likelihood estimate. So when we take the derivative and set it to 0, what we will get is the maximum likelihood estimate of w, and that will be precisely x transpose x inverse, okay, x transpose times t vector. This is the t vector. Okay, let's unpack it a bit. So here what we have is x transpose x, right? So what is x? X, the dimension of x is n times d. X transpose will be d times n. So this entire thing will be d cross d, and we will take its inverse. Okay, and then it will be multiplied with something that is d cross n, and then we have n cross 1. Okay, so entire thing will be same as what we will get here, d cross 1. So these are the d different weights that we want. So the entire dimensions of the matrix multiplication check out quite nicely. But now there is something more to it than what meets the eye. So in general, you will have n that is greater than d. Okay, n greater than equal to d at least. Why is that? Because otherwise we'll have an underdetermined system where we have more unknowns than the number of equations. So if n is greater than equal to d, then we have an overdetermined system and we will not have an exact solution. What that means is that our error will never be 0, but the sum of squared of the errors is going to be the minimum. Okay, so we will find a solution where we will have the sum of squared of errors that is going to be the minimum, and that is precisely what we started out to do with this. Okay, now this quantity, this x transpose x whole inverse times x transpose, is called a pseudo inverse of x, right? You can think of it this way: if you have t is equal to x times w, if we pre-multiply both with x inverse, we would get the t back. right? But we cannot multiply with x inverse. X is not an invertible matrix, so we multiply it with the pseudo inverse of x, and that will give us, when we multiply that with t, we will get the maximum likelihood estimate of the w's back. Now there's a problem with this. We will talk about the problems in this analytical solution. Now if you look at this particular pseudo inverse, x transpose x inverse times x, right? So here we are inverting a D cross D matrix, right? So what is the order of number of operations required to invert this matrix? So if we do any kind of triangulation of the matrices or any other such analytical method, the order can be order D cubed. Okay, we will need the number of operations that are proportional to d to the power 3. Okay, that will be the function will grow as d to the power 3. Now if you have a whole lot of if you have a very large dimensional matrix where this d is let's say 10,000 or something along those lines, then order d cubed is a very expensive operation to conduct. Also, it could be that the rank of the matrix is close to, it's less than the full rank, and then you have numerical stability problems in inverting this matrix. With smarter methods, you can go up to order d to the power 2.6 or something, 2.6, 2.7. Even that is quite expensive when d is large. So what we need to do is we need to find a computational method that can give us the same solution but without having to do d cubed number of operations or order d cubed number of operations. Okay, and this is where what we do is we start to use gradient descent. So in gradient descent, first of all, gradient descent works only for convex problems, but it should be obvious that if you are minimizing the sum of squared errors, then it's a convex problem in W. Okay, it's a convex function of W. So basically what we need to do is we need to update W by taking, so let's say this is your previous W. We will take some eta, which is a step size, or minus rather, because we are minimizing, and we will take the gradient with respect to W of that loss function, which is the sum of squared errors. Okay. And we will do this iteratively. Okay, so we saw this in one of the earlier lectures, that gradient descent leads to the minimization of convex functions. And here basically what we will get is, when we compute this derivative, we will get that W, the update equation for W will be this step size, but here then we will have a sum over I is equal to 1 to n. Okay, and we will have Ti minus W transpose x xi times xi. Okay. So this is d cross 1, this is d cross 1, and this is a scalar, so this is 1 cross 1, and this is again d cross 1. So always ensure that your dimensions match out. And this is nothing but the summation, and everything else that you see is the negative of the gradient. So here the only thing that we need to determine is what is a good step size, and as we have seen earlier, that if the step size is too small, we will require too many steps for gradient descent. If the step size is too large, then we will overshoot and we will actually increase the loss as opposed to decreasing the loss.